Let's look at inverse trig functions. So let's start with the inverse sine function. So if you remember from our last video, the way that inverse functions work is, at least graphically, if a horizontal line passes through only one point at every point in the domain, then our function is one-to-one, which means it does have an inverse. So if that's the case, how do any of our trig functions have inverses? Because none of them would pass the horizontal line test. And we can see that demonstrated quite clearly here with sine, where if we look at our sine function, even if we looked at it only over one period from 0 to 2 pi, it would still fail if we let a horizontal line go through 0. So something is not going to work with that if we wanted to have an inverse of sine. So instead what we do is we limit it to half of our period. And in this case, we're simply going to take the part that goes from negative pi over 2 to pi over 2. So this part that we have highlighted here in blue, and in fact, I'll just draw it in a little bit more right here in blue. So we're going to take just that piece. And if you remember from algebra and from our test for symmetry, it looks as if we have an odd function here, which is good because sine is still an odd function. So the reason why we're going to take it around this period here, this half a period, is because this particular one is also going to maintain that odd nature of sine. So remember, for an odd function, if we remember that, it means that f of negative x is equal to negative f of x. It also means, this is an odd function, it also means that our function is symmetric about the origin, which we still have. So we're maintaining some of the properties of sine while still being able to limit its domain in a way that we will be able to find an inverse. So instead, we're just going to look at the domain of our function being between negative pi over 2 and pi over 2. So if we look at the domain of sine, so our function, we're only going to look at negative pi over 2 to pi over 2, and our range is going to stick with negative 1 to 1. So now remember, our sine function already has a range of negative 1 to 1, so we didn't really change anything. And if you remember from our last video, or if you remember from algebra, remember that when we find our inverse function, that we are rotating about the line y equals x, and we are inverting our x and y values. So that means we also invert our domain and range, which means our domain of our inverse is going to be negative 1 to 1, and the range of our inverse is going to be negative pi over 2 to pi over 2. We're going to see that a little bit more on the next slide. So here we are. This is our inverse of sine. So an equation for the inverse of f of x or y equaling sine x can be found by interchanging x and y. So we would change it to x equals the sine of y, which we can see right here. X equals the sine of y. And we're keeping our y between negative pi over 2 and pi over 2, which we'd already said we were going to do because now we're switching them around. The explicit form here would be called the inverse. This is our implicit form. So in other words, our explicit means we have to solve for y. And then we switch the x and y back. That's how inverses work. It's a little bit crazy, but if you remember, what happens is to find an inverse, right? To find the inverse, you switch your x and y and solve for the new y. And that is your inverse. That's our f inverse. So if that were the case, and we switch them around from y equals the sine of x to x equals the sine of y, we now have to find a way to solve for y. I liken this to a similar process with logs and exponentials. So you remember with logs, we have that log base b of y equals x if and only if b to the x equals y. and it goes backwards, it goes both directions. So b to the x is equal to y if and only if log base b of y equals x. And I find this is a similar thing when we start looking at these inverse trig functions, because we would say y is equal to, and here's our new function. We have this inverse sine. So y is equal to the inverse sine of x if and only if x is equal to the sine of y. So it's very similar. We would say that y, change pens here. So y equals the inverse sine of x, right, of x, if and only if x equals the sine of y. And what we're going to do is we're going to be seeing that essentially when I do want you to evaluate an inverse sine, it means what angle has the sine that is that number that you're taking the inverse sine of. What does it graphically look like? It's not a surprise. It looks the same as any other inverse. You switch your x's and y's, connect them in the same way that it looks like it was around the line y equals x. And I have a picture there for you. And notice that indeed the domain of our inverse, right, is now negative 1 to 1. And the range of our inverse is now negative pi over 2 to pi over 2. Right? And I know that might be a little confusing because I did them in the exact opposite colors. The graph. Sorry, I should have thought ahead about that one a little bit more. But I already went with it because we did the inverse in red on the previous slide. But this is what it looks like. So how does this work in practice? Well, if I wanted to find the exact value of the inverse sine of negative 1 and the inverse sine of, and I meant to make this a positive 3/2, you'll see on cosine I meant negative root 3 over 2. And this one I meant the positive. So what we're going to do is we're going to call this one A and this one B. And what we're really looking for here is we want to say, if A says, what is the inverse sine of negative 1? Then we'll say, okay, if I say inverse sine of negative 1, I'm going to call it some angle theta. I don't know what theta is yet, but that's what I'm trying to solve for. But this is true if and only if the sine of theta is negative 1 and theta is between negative pi over 2 and positive pi over 2. So it's if and only if sine of theta is equal to negative 1 and negative pi over 2 is less than or equal to theta, which is less than or equal to positive pi over 2. And this is where things can get tricky, and I did pick one of the trickier ones to start with, because what I'm asking essentially is what angle has a sine that is negative 1? And if we think about our unit circle, we're looking at this angle down here, right? Because this coordinate is 0, negative 1. And remember, your unit circle is in cosine sine, are your coordinates. And so that's where sine is negative 1. And if you think about this angle then, in the positive direction, that's going to be 3 pi over 2. However, 3 pi over 2 is not between negative pi over 2 and positive pi over 2. So instead of using the positive angle, we're going to use the negative angle, the negative coterminal angle, which would be negative pi over 2. So in this case, because 3 pi over 2 is not in quadrant 1 or quadrant 4, we need to use the negative angle. We need to use theta equal to negative pi over 2 instead. So we're using the coterminal negative pi over 2. Now, not all of our questions are going to be that complicated, but I wanted to get one of the more complicated decision-making kind of questions out of the way first, because some of them will be pretty straightforward. So if we were to look at, say, let's look at B here. We know that we've got inverse sine of, and like I said, I want to make it positive root 3 over 2. So I said the inverse sine of positive root 3 over 2 is equal to theta. That is true if and only if the sine of theta is equal to root 3 over 2. And theta is in quadrant 4 or quadrant 1, right? So it's between negative pi over 2 and pi over 2. So what we want to know is what angle has a sine that is root 3 over 2. Well, back we go to our unit circle. So root 3 over 2 means that our sine value is root 3 over 2, so we went over a little and up a lot. So this is our 1/2 and our root 3 over 2. That means our theta is a 60-degree angle, which is pi over 3. And the nice thing is we don't have to worry about now our sine needing to be, or our angle needing to be positive or negative, because pi over 3 is between negative pi over 2 and pi over 2. And it couldn't be in quadrant 4 because in quadrant 4, sine is negative. So it can only be in quadrant 1. So we're okay. It fits the proper domain for our inverse, and we have now found our angle that has a sine of root 3 over 2. For the next example, we're going to look at how to find the approximate value of an inverse sine of a different number that's not on the unit circle. So you hit second, sine, put in your 1/3, and we end up finding 19.47. Now let's go to mode and see. That is in degrees. What if we want it in radians? Well, let's change it back to radians. And then we're going to try again. So we'll hit second enter, or you can hit up and enter, and just try it again. And in radians, we have 0.34. So we have that the inverse sine of 1/3 is equal to 19.47 degrees, or 0.34 radians. So it'll be either one. Now I don't have a video of the second one, but what I'd like for you to try on your own is to see if you can replicate my results if we did inverse sine of 1/4 instead. And you plug it into your calculator, pause here, use your inverse sine function on your calculator and see, as long as you're in degrees first or in radians, pick one and start with it and then do the other one. See if you get the same numbers. So maybe pause and then come back and see if you get the same answers. If you found the inverse sine of 1/4 in degrees, you should get negative 14.48 degrees. And if that would also be the same as a negative 0.25 radians. These are the values that I found using my calculator. I hope that you can replicate these with yours as well. If you get stuck on something, make sure you ask me about it in class on Monday. As we continue to study inverse functions, now let's look at inverse cosine. So in the same way that we couldn't use the entire sine function because it did not have an inverse because it wasn't 1-to-1, cosine fits the same bill. So instead, what we're going to use for cosine instead is we're just going to use the half a period that goes from x equals 0 to x equals pi. So we're going to do 0 to pi instead of 0 to 2 pi. So we're just going to look at x equals 0 to x equals pi. So our domain of our function here, domain of our function, is then going to just be this restricted domain of 0 to pi. And our range is still negative 1 to 1, as it always has been. So that way, when we switch to our inverse, remember we're going to switch the domain and range, we'll now have a domain of the inverse will be negative 1 to 1. And the range of the inverse will now be 0 to pi. So we'll see that on the next page. So now that we have seen an inverse sine, Inverse cosine follows by the same general idea. So an equation for the inverse of y equals f of x, which is cosine of x, can be found by interchanging the x and y. So again, our implicit now is x equals cosine y, where y is between 0 and pi, and x is between -1 and 1. So this explicit form then is called the inverse cosine, which is the same thing that we saw with inverse sine, but now we've got inverse cosine, which just looks like it has to a -1. So, and again, in the same way that sine worked, cosine works the same way. Our inverse sine and inverse cosine works the same. So essentially, if y is the inverse cosine of x, that's true if and only if x is equal to the cosine of y. So essentially, we're looking for the angle that has that specific value of cosine. So we're going to practice with a couple. So find the exact value of the cosine inverse of 1/2, the inverse cosine of 1/2. So we'll call this A, and we'll also do inverse cosine of negative √3/2. This time I did mean to keep the negative. So let's find the exact value of the inverse cosine of 1/2. So for A, we have the inverse cosine of 1/2 is equal to theta if and only if cosine theta equals 1/2, and theta has to be between what two values? 0 and pi. When we get to inverse tangent, you'll find out it has the same restriction on theta that sine does. So cosines really are standalone in this case with the 0 to pi. So we're looking for an angle that has a cosine that is 1/2, and the angles between 0 and pi. So we think back to our unit circle. We have a cosine that is 1/2, which means that the sine is √3/2. This would give us a 60-degree angle, which is pi over 3. So theta here would be pi over 3. So now, yes, this cosine could also be a negative 60 degrees or negative pi over 3, but remember that negative pi over 3 is not an allowable value for theta. Theta has to be between 0 and pi. It has to be in quadrants 1 or 2. So we can only have a positive cosine in quadrant 1. So we only can have quadrant 1 or quadrant 2 for inverse cosine. So in this case, we have to stick with our pi over 3. Now what happens if we switch it to a negative? So now we have the inverse cosine of the negative √3/2, and that is our theta if and only if the cosine of theta is equal to negative √3/2, and theta is between 0 and pi. So just like we had before, we had quadrants 1 and 2. That's what we're looking for. We're still looking for quadrants 1 and 2. So let's see if we can figure it out. Well, cosine being negative is immediately going to take us out of quadrant 1. So we can know that right away, because negative cosine means it has to be in quadrant 2. So we're looking back here at quadrant 2. We have a negative √3/2, which means it goes up a smaller amount, which would be our 1/2. That's going to be our 30-degree angle above 180. So it's 150 degrees, which is the same as 5 pi over 6. So in this case, our theta here is 5 pi over 6. Yes, there could also be another angle in quadrant 3 that also has a cosine that is a negative √3/2, but again, it's in the wrong quadrant. So we have to bear in mind what values of theta are allowable for each kind of inverse function. We have one last inverse function, and that is the inverse tangent. And by now, we know that it's not inherently one-to-one. We already know we're going to have to limit the input. So we're going to limit our domain on our tangent to be between negative pi over 2 and pi over 2, and that keeps its odd nature, just like it did with sine. We're still symmetric around the origin here. F of negative x is still negative f of x. And so what we notice here, and I believe I put a small typo there, it should be parentheses, not brackets there. So please mark that change on your paper. So we were going to restrict our domain now to the interval from negative pi over 2 to pi over 2, not inclusive, because remember that's where we have our two vertical asymptotes. So bear in mind that we have vertical asymptotes at x equals negative pi over 2 and positive pi over 2, right? And so when we now take our domain of our function, right, which there's really not a great way to say this. This is really all real numbers except x cannot be multiples of pi over 2. So it can't be, if we notice again, pi over 2, 3 pi over 2, 5 pi over 2. So x cannot be odd values, or odd multiples, I should say. Odd multiples of pi over 2. Kind of an odd thing to say, but it is what it is. We've been through this already before. We've already looked at our graph of tangent, so we know it's a little bit odd. And then we know that our range for tangent is really all real numbers. And so when we start talking about our inverse here, the domain is going to be all real numbers, right? So our domain for our inverse will be all real numbers, so negative infinity to infinity. And our range of our inverse is now going to be y cannot equal odd multiples of pi over 2. So that tells us that something is a little strange. Well, remember, that also means if I had vertical asymptotes at x equals, they now become horizontal asymptotes at y equals negative pi over 2 and pi over 2. So we've taken this whole thing and flipped it. What does that look like when we put it all together? It looks like this. So the red is our tangent and the blue is our inverse tangent. So notice that we can have any value of x we want going down to negative infinity, any value of x we want going to positive infinity, but see these horizontal asymptotes? Here, we'll highlight them. These horizontal asymptotes go straight through here and here. And so our blue function is what we're really looking for. Is it staying in between? Oh, let me make that a different color. We'll take off that color. So it's not, we'll make it maybe a darker blue. How about that? Let's highlight that in a slightly darker color. There we go. There's our inverse tangent function. And it continues off to infinity in the x direction, both positive and negative. But it is limited by those two horizontal asymptotes at pi over 2 and negative pi over 2. So we have to remember now that things are going to be just a little different here. Now y, or in our case theta, is going to be limited again by negative pi over 2 to pi over 2. So it's a little different than we're used to dealing with tangent. And so what we have going for us is that y is the inverse tangent of x if and only if x is equal to tangent of y. X can be any value, but y has to be between negative pi over 2 and pi over 2. And of course, we're going to now do a couple of examples of finding an inverse tangent, and then we're going to wrap up this section so you can finish homework 10. So let's find the inverse tangent of negative root 3 over 3. So let's see here. So we know that inverse tangent of negative root 3 over 3 is some angle theta if and only if the tangent of theta is equal to negative root 3 over 3 and theta is between negative pi over 2 and pi over 2. So that's what we have to remember. So here's the thing to remember is that if tangent is negative root 3 over 3, that's the same as saying that was really a negative 1 over root 3 before we rationalized it. And the way I like to think of this one is, okay, if I've got a tangent of theta that is equal to negative 1 over root 3. It came from a negative, I'm not sure if it's going to go with a 1/2 or the root 3 over 2, but it was a 1/2 and it was a root 3 over 2. So we need to find an angle that uses 1/2 and root 3 over 2. So we know we're looking at a pi over 6 or a pi over 3 in one of our quadrants. And we're only looking at quadrants 1 and 4 again, right? So we're looking at quadrant 1 and quadrant 4. Our tangent is negative, so that's telling us already that we're not going to be in quadrant 1. We're going to be in quadrant 4. So our tangent here is negative. So theta is in quadrant 4. So we already know we're going to have a negative value here. So what we need to know is that tangent is equal to sine over cosine. So it tells us here that sine theta is 1/2 and cosine theta is root 3 over 2. But now we have to figure out which one is which in terms of the sign, positive or negative sign that is. But we know that our angle is in the fourth quadrant. And we know that cosine is root 3 over 2, so it's going to go over longer than it goes down. So we have a positive root 3 over 2, and there's the negative. It goes with the 1/2. So sine is negative 1/2, cosine is root 3 over 2. This is a negative 30 degrees or a negative pi over 6. So in this case, theta is a negative pi over 6. And why would we call it a negative pi over 6 versus an 11 pi over 6? Because it has to be between negative pi over 2 and positive pi over 2 in order for our inverse tangent to exist. So with that, we've wrapped up our section on inverse functions, inverse trig functions, and practiced each. So you can go ahead and finish homework 10, and we'll catch up with a couple of extra problems to try together on Monday.